Good morning, friends. It gives me immense pleasure to be here again for my course Engineering Thermodynamics. I am at the last module, module number 5, and today I am in the 6th lecture of module 5. This module 5 belongs to the heat transfer and gas compressors. As of now, I have completed the 4th module. The first module is basic properties of the thermodynamics. In that, we have learned about pressure, temperature, volume, entropy, enthalpy, work and heat, 0th law of thermodynamics, first law of thermodynamics, and the relation between heat and the work. If you talk about the module 2, we have learned about second law of thermodynamics. In that, we have discussed about the efficiency of the system, because you cannot raise the temperature from lower temperature to higher temperature without adding some external work. That is the definition of the second law of thermodynamics, and this gives about the efficiency. It means if you give some energy for any system, that system will not produce the same amount of work as you supply the heat. There will be some losses, and these losses are accounted with respect to the efficiency, and we know the efficiency of any system is always less than 1 or 100%. In respect of this, the Carnot has devised a cycle in that for a given temperature range of high and low temperatures, the maximum efficiency can be produced by the Carnot cycle. And in the Carnot cycle, we have the 2 reversible adiabatic or isentropic process, and 2 we have the isothermal processes. And by that, we can get the maximum efficiency. If any cycle which we make it, and if it is giving more than the Carnot cycle, it is impossible, and it means that is a perpetual motion machine. Always we have to, whenever we design any thermal system or engines or this heat exchangers or any turbine compressors and all, we should always keep in mind that the ideal case will be when the processes are taking place ideal. Means if it is a compression and the expansion, they should be in reversible adiabatic or isentropic process, and other process, it may be isothermal or the isobaric or the isochoric process. It should be the ideal conditions. But in the real field, you won't get the ideal condition. So these things we have studied in our module 2, that is the second law of thermodynamics. In module 3, we have discussed about psychometric TS and HS diagram, how to find the dry bulb temperature, wet bulb temperature, and humidity of the systems and the surrounding, that we have done it. In the 4th module, we have done about the power cycle. If you talk about the power cycle, these cycles are used for generation of the work. We can divide this cycle into the 2 groups. One is the power generating cycles, another is a power absorbing cycle. So in the power generating cycle, we can further divide into the 2 groups. One is the reciprocating type, another is a rotary type. So in the reciprocating type of cycle, we have seen the Otto cycle, diesel cycle, and the dual cycle. And for the rotary type of engine, we have seen the Brayton cycle. Mostly this Brayton cycle are used for the turbine engines. All this nowadays power plants, aircrafts, submarines, ships, they use the gas turbine engine. In gas turbine engine, the Brayton cycle is used. And these all 4 cycles are power producing cycle. Another important cycle is power absorbing cycle. This cycle can be used for the refrigeration and air conditioning, and also this can be used for heat pump. These heat pumps are used for the heating the environment or room or the building. In cold countries where the temperature is very low, Canada and Siberia, Russia and some other countries, we use this heat pump. These heat pumps are much better than the using the electrical devices to heat the rooms and all. So if we use these cycles for heating or the cooling of the system, that cycle name is Bell-Coleman cycle. This Bell-Coleman cycle is used for the refrigeration and air conditioning of aircraft, rooms, submarines, ships, automobiles, and so many places nowadays. This refrigeration and air conditionings are used. As of now, in module 5, we have the heat transfer and the compressors. In heat transfer, we have done with conduction, convection, radiation, and we have also done with some numericals of these things. And now we will see the heat transfer mechanism with one numerical we will be trying to do in this class. So in my today's lecture, what are the topic which I am going to take? It is part of this content. So here we will have simultaneous heat transfer mechanism. We will see that if it is a different types of composites. Yesterday we have seen the this resistance of one solid piece, then one hot fluid to the metal, then from metal to the air. Like this we have seen the resistance method, that how we will do. Now we will do the another thing with a simultaneous heat transfer mechanism. Then we will see the numerical one. It is heat transfer from human body to the atmosphere. Then we will see the numerical 2 heat transfer from human body to the atmosphere. Another one. So in my last class, I have discussed about 1D steady state heat transfer. In that we have seen that how this heat transfer is taking place in the one direction. In this, the perpendicular area of that direction is very important to find out the rate of heat transfer that we have discussed. Derivation of the 1D equation we have already completed. Resistance offered by the conduction, this we have seen that this R by the conduction is equal to L by Ka. This we have already derived also, and we have done this thing. Resistance offered by the convection, so Rc is equal to 1 by Ha. This also we have find out in my last class. Total resistance is in multiple phases. So if we have the number of phases, so if we have this is the solid, and here is the hot fluid with H1 as a thermal conductivity for this conductive, and here is the air, atmosphere, and this is the solid. Okay, so this is the H1 and this is the H2. So if this is the T infinity 1 and this is the T infinity 2, so this is the T1 here, this is the T2 here. So here we can see that this is the T infinity 1, this is the T1, this is the T2, and this is the T infinity 2. So like this we can see that this R is equal to 1 by H1A plus 1 by K1 L by K1A, if this is the L, plus 1 by H2A. So this is the total resistance of the system we have done in our last class. Now total resistance in composite wall, if there are number of walls here, number of wall, that also we have done in the same way, which we can do and which we have done already in my next class. Please refer my next class, previous class. Please refer my previous class regarding all these topics to understand well before you go for this lecture. Now I am taking the topic, simultaneous heat transfer mechanism. So in this, there are three mechanisms of heat transfer, but not all three can exist simultaneously in a medium. We know that three mechanisms: heat transfer, conduction, convection, and the radiation, and may or may not exist all the three at a time in any medium. For example, heat transfer is only by conduction in opaque solids, but by the conduction and the radiation in semi-transparent solid. So if we take a heat transfer only by the conduction is opaque solid. So if it is a very dense solid like this, only conduction will be there. Only the conduction will take place, but conduction and radiation in semi-transparent solid. So if this solid is semi-transparent, it is solid, and if it is the semi-solid, I will write semi-transparent solid, then the conduction and the radiation. So the radiation, it is called the radiation, and from here to here it will flow. It is called the conduction. From T1 to T2, it is the conduction, and after this it will emit the energy. So it is a radiation. So here radiation and the conduction will happen simultaneously. Thus, a solid may involve conduction and the radiation, but not convection. So if only solid is there and it is heated, so this solid will only have conduction and the radiation. This convection will not happen. Convection is only will happen whenever there is a fluid is involved. If some fluid is here or here, then only convection will take place. However, a solid may involve heat transfer by convection and or radiation on its surface exposed to fluid or other surfaces. So if this solid which I have shown here, here we have some liquid like hot water. This is the hot water, and here we have the air. So this can be involved all the three, that is the conduction, convection, and the radiation. And if totally it is covered, this solid, the hot solid is totally covered the fluid, radiation may not be there, and it will be only the conduction and convection will take place. So simultaneously means there may be conduction or the convection or the radiation, or it may be the conduction and the convection, or conduction and the radiation, or conduction, radiation and convection, or may happen. For example, the outer surface of a cold piece of a rock will warm up in a warmer environment as a result of heat gain by convection from the air and the radiation from the sun or the warmer surrounding surfaces. So if you see here, if this is the rock, the outer surface of a solid piece of a rock, okay, this is the rock, so will warm up in a warmer environment. So if it is the hot sun is here, it is a sun, so it may be hot up in the warmer environment as a result of heat gain by the convection from the air. So it is the hot air in the summer. This hot air will be heating, and the radiation from the sun or the warmer surrounding surfaces. So it is a sun. So from sun you will get, or from hot air. So it may be heated by the convection and by the radiation. So this rock can be heated, but the inner part of the rock will warm up as this heat is transferred to the inner region of the rock by the conduction. But this is only will be affecting, radiation will only affect at the surface. I am just putting the different colors. So okay, so this you can see here, this is the, this much only it will be heating. So inside this it will move, the heat will move, and this will be by the conduction. So at a time simultaneously all the process may happen. Conduction, convection and the radiation may happen, but we have to see that in which phase what is happening. That is the objective of our learning. Now we can see that heat transfer is by conduction and possibly by radiation in a still fluid, no bulk fluid. So if there is no fluid is available, so the heat transfer will take place by the conduction and the radiation, and by convection and radiation in a flowing fluid. So if the fluid is available, then convection will take place. If fluid is not there, then only conduction and the radiation. Without fluid, only conduction and radiation. With fluid, conduction and convection will take place. In the absence of radiation, heat transfer through a fluid is either by conduction or the convection. If the radiation is not there, then the conduction heat transfer will take place through conduction or the convection, depending on the presence of any bulk fluid motion. If the bulk fluid is there, then conduction and the convection will be there. If bulk fluid is not there, only the material is available, a hot material, then only conduction will take place. Convection can be viewed as a combined conduction and fluid motion, and conduction in a fluid can be viewed as a special case for convection in the absence of any fluid motion. So if fluid motion is not there, we can see that the convection can be viewed as a combined conduction and the fluid motion. So here this you can see it is opaque solid. So here the conduction is taking place. So only one mode is there, T1 to T2. Only in this material heat is transferred. So it is called the Q. So Q is from here to here. It is a single mode. If you see another one, there is a T1 temperature. Here is the gas. Here is the radiation and the conduction or the convection. So here we have the two mode. One is a radiation and another is conduction or convection. Another one is here, if it is a vacuum, only radiation will be there. Like here you have the sun and here you have the earth. So like this, earth temperature is T2 and sun is T1 and there is a vacuum, only the radiation will take place. So these all three, one mode, two mode and another one mode, this can happen. When we deal with heat transfer through a fluid, we have either conduction or the convection, but not both. So if we are taking the heat transfer through a fluid, so we will have the conduction or the convection, but both will not be present. So this you can see here, conduction or convection. Only one will be there, both will not be there. Also, gases are practically transparent to radiation, except that some gases are known to absorb radiation strongly at certain wavelength. So mostly the gases are not affected by the radiation, but few gases they are able to absorb the radiation for a certain wavelength of the radiation. Like ozone absorbs UV radiation. Ozone is the gas which absorbs the UV radiation. Now I will go for one numerical. That numerical is very interesting numerical, and it is a real problem, and how we can solve this problem we will be trying to understand by this numerical. So it is common experience to feel chilly in winter and warm in summer in our homes, even when the thermostat setting is kept the same. Means if it is air conditioner, you are putting the 20 degree. And if you are putting the 20 degree at summer, you will feel it is cool, but the 20 degree at winter, you will feel that it is a chilling. Because outside ambient temperature is 10 degree. So it is depend upon the situation. This is due to the so-called radiation effect resulting from radiation heat exchange between our body and the surrounding surface of the walls and the ceiling. So this is happening due to the radiation effect. This radiation effect will happen between the body and the surrounding surface of the walls and the ceiling. So consider a person standing in a room maintained at 22 degrees centigrade at all times. The inner surface of the walls, floors and the ceiling of the house are observed to be an average temperature of 10 degrees centigrade in winter and 25 degrees centigrade in summer. Determine the rate of radiation heat transfer between this person and the surrounding surfaces. If the exposed surface area and the average outer surface temperature of the person are 1.5 meter square and 30 degrees centigrade respectively. The emissivity of a person is, that is epsilon is equal to 0.95. So I will reread it. A person is standing in a room. That room temperature is 22 degrees centigrade at all times. The inner surface of the wall, floor and the ceiling of the house are observed to be an average temperature of 10 degrees centigrade. So the room temperature is hotter than the wall temperature in winter and 25 degrees centigrade in summer. So means in summer you are observing as a 25 degrees centigrade and in winter it is 10 degrees centigrade, the wall and your boundary of the room. So determine the rate of radiation heat transfer between this person and the surrounding surface if the exposed surface area and the average outer surface temperature of the person area is the man who is standing is 1.5 meter square and its temperature is 30 degrees centigrade respectively. So these are the parameters which are given for our problem. So here you can see this is the person, the temperature of the person is 30 degrees centigrade and its area is 1.5 meter square. Q dot radiation, it is emitting from person to the wall. T surrounding is given. This all as per summer and the winter, this all conditions are given. So now we have to find out the rate of radiation between the person and the surrounding. So the rate of radiation heat transfer between a person and the surrounding surfaces at specified temperatures are to be determined in summer and the winter. So we have to determine the rate of radiation in the summer and the winter, which we will be observing here. The net rates of radiation heat transfer from the body to the surrounding walls, ceiling and the floor in winter and the summer are, we can write like this, the radiation, that is Q dot radiation in winter is equal to epsilon sigma As Ts to the power 4 minus T to the power 4 surrounding in winter. So we have to see the right here winter. First we are considering the winter condition. So now you can see here that epsilon is given 0.95. This sigma is 5.67 into 10 to the power minus 8 watt per meter square, K to the power 4. Then area is 1.5 meter square temperature of the surface during the of the person is 30 degrees centigrade plus 273 minus 10 plus 273 to the power 4. This will come as a k to the power 4. These are known. Area is given. 30 degree is a human temperature, and this is the wall temperature in winter. Okay, so this you will get 152 watt. So for the winter, the rate of heat transfer is 152 watt. Now we will see for the summer, and Q dot radiation for the summer is equal to epsilon sigma as Ts to the power 4 minus T to the power 4 surrounding in summer. So here epsilon is same 0.94. This is also same 5.67 into 10 to the power minus 8 watt per meter square. K to the power 4. 1.4 meter square is the area. Human temperature is 30 plus 273 to the power 4 minus the surrounding temperature of the wall is at the summer. This is for the summer condition. Summer wall temperature, and this is the human temperature. So this will radiate, the human will radiate from 30 degrees centigrade to 25. So we have to take in Kelvin. So 30 plus 273 to the power 4 minus 25 plus 273 to the power 4. So you will get the answer as a 40.9 watt. So you can see that here in the summer the temperature difference is more. So more heat transfer will take place in winter. But in summer it is very less. I think it is nearly 1/3. So discussion, we must use absolute temperature in radiation calculation. So we have to use the Kelvin K as a unit. So if it is the centigrade, use C plus 273 Kelvin. This has to be always remembered. So we can see here that also note that the rate of heat loss from the person by radiation is almost 4 times as large in winter than it is in summer, which explains the chill we feel in winter even if the thermostat setting is kept the same. So in winter we feel the chill because the heat transfer in the winter is very high comparing to the summer. So in winter we feel the chilling effect. However, we have set the same temperature. So this is the discussion on this topic. I am going to take this second problem. First problem, we have seen that how a human can radiate the heat, and we have seen that in winter, being the same thermostat setting of the air conditioner, in winter we will feel more chilling because the rate of heat transfer is more in the winter. And hope you have understood that problem. Consider a person. So now I will take the second one. Consider a person standing in a breezy room at 20 degrees centigrade. Determine the total rate of heat transfer from this person if the exposed surface area and the average outer surface temperature of the persons are 1.6 meter square and 29 degrees centigrade respectively, and the convection heat transfer coefficient is 6 watt per meter square Kelvin. the emissivity of a person is 0.95. So here the person is standing in a breezy, the room temperature is 20 degrees centigrade. We have to find out the total heat transfer Q from this person if the exposed surface area and the average outer temperature. So area is 1.6 meter square and the temperature of the person is 29 degrees centigrade and the convection heat transfer coefficient H is equal to this. The emissivity of the person is 0.95. So now we have to find out the same way. This is the diagram here. Here we have the room. Room temperature is 20 degrees centigrade. So 20 plus 273, 293 Kelvin. Here the body temperature is 29 plus 273. So it is 302 Kelvin. And it is radiating. So we have to find out how much convective heat transfer is present in this case. So now we will go for the solution. The total rate of heat transfer from a person by both convection and radiation to the surrounding air and the surfaces at a specified temperature is to be determined. So heat transfer by the convection and the heat transfer by the radiation we have to find out to the surrounding air and the surfaces at a specified temperature to be determined. That we have to find out first. Then we will see that analysis part. The heat transfer between the person and the air in the room is by convection instead of conduction. So if you can see this diagram here, it is the convection. Here the convection is taking place because it is moving by the air. Temperature is moving by the air. We cannot assume it as a conduction. So we have to see that the heat transfer between the person and the air in the room is by the convection. This is not there. Conduction is, we should not take, since it is conceivable that the air in the vicinity of the skin or the clothing warms up and rises as a result of heat transfer from the body, initiating natural convection current. So if the body temperature is higher, this body temperature will go to the air and the temperature of the air, the surrounding which is for the human being will go up. So that is the, we are assuming, and it is happening also. So now it appears that the experimentally determined value for the rate of convection heat transfer in this case is 6 watt per unit surface area. So this is the value is given 6 watt per unit area per unit temperature difference in Kelvin or degree centigrade between the person and the air away from the person. Thus, the rate of convection heat transfer from the person to the air in the room is given by Q dot convection is equal to HAS Ts minus T infinity. So here H is given, A is given, these temperatures are already given. So we know that H is 6 watt per meter square degree centigrade into 1.6, area is 1.6 meter square. Ts is equal to 29 degree centigrade minus 20. So you will get the answer as 86.4 watt. So this is the heat transfer takes place due to convection. We cannot use here conduction. Okay. Now, the person also loses heat by the radiation to the surrounding wall surfaces. So the person has got some heat and that heat will be also emitted as a form of radiation. So we have to understand about the radiation. We take the temperature of the surface of the wall, ceiling and the floor in this case to be equal to the air temperature in this case for simplicity, but we recognize that this does not need to be the case. And we will see that the air temperature and the wall temperature are the same, but in the real scenario it may not be same. These surfaces may be at a higher or the lower temperature than the average temperature of the room air, depending on the outdoor condition and the structure of the wall. So your air of inside the room and the walls may not be same, because if the outer side it is hot, then your walls will be hotter than the air, and if the outer side is cool, so air will be hotter than the walls. So we are taking assumption that it is a same temperature outside and the air and the walls are in the same temperature. Considering that air does not intervene with the radiation and the person is completely enclosed by the surrounding surfaces, the net rate of radiation heat transfer from the person to the surrounding walls, ceiling and floor is given by Q dot radiation is equal to epsilon sigma as Ts to the power 4 minus T surrounding to the power 4. So here epsilon is equal to 0.95 and this sigma is equal to 5.67 into 10 to the power minus 8 watt per meter square. K to the power 4. Area is equal to 1.6 meter square. Temperature is 29 plus 273 to the power 4 minus 20 plus 273 to the power, and it is K to the power 4. So you will get the answer is 81.7 watt. Okay, so you got the answer 81.7 watt. So then the rate of total heat transfer from the body is determined by adding these two quantities. So by the convection how much heat is added and heat transfer, and by the radiation how much heat, then we have to sum up these two things. So Q dot total is equal to Q dot convection plus Q dot radiation. So in convection we got 86.4 and by the radiation we got 81.7 watt. So total radiation is 160 watt. So this is the total heat radiation of this human from human to the surrounding. These things are happening. Now we will discuss this answer, and this we will see that the heat transfer would be much higher if the person were not dressed, since the exposed surface temperature would be higher. So if you are dressed, if you are wearing the cloth, then your heat transfer will be less, and if you are not wearing the cloth, then your heat transfer will be very high. Thus, an important function of the cloths is to serve as a barrier against heat transfer. So what is the important function of the cloth? Is to serve barrier against the heat transfer. Okay, so we have to wear the cloth in any season. It may be summer or the winter or anything. Your cloth will always give the better feeling and your heat reduction from the body will be reduced. In this calculation, heat transfer through the feet to the floor by the conduction, which is usually very small, is neglected. Heat transfer from the skin by the perspiration, which is the dominant mode of heat transfer in hot environment, is not considered here. So by the sweating, we have not considered. Only the emission or emitted things are only considered. Also the units watt per meter square degree centigrade and watt meter square Kelvin for heat transfer coefficient are equivalent and can be interchanged. So now just some images I have posted here about the heat exchangers. In next class I will be discussing about introduction to heat exchanger. types of heat exchanger, illustration of double pipe heat exchanger, cell and tube heat exchanger, multi-pass heat exchanger, plate heat exchanger, regenerative heat exchanger. These are the references which I have taken from P.K. Nag, Engineering Thermodynamics, McGraw-Hill's. Then Yunus Senegal, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw-Hill's. Any questions, you are welcome to ask. My email is ydwedi@gmail.com. So you can ask any question. Also, I request to like and subscribe my channel. Thank you very much for joining my class. Please do log in for my next class, which is about the heat exchanger. I am going to discuss in my next class very soon about the heat exchanger. Till then, goodbye. See you.
Like, share and subscribe. Hit the bell icon for more updates.